Hello, this is Nathan Smith. I'm recording this for my students in managerial economics in Visalia and North Fresno, and this is an explanation of the homework problems for the third set of homework problems, so chapters 6, 7, and 8. So, okay, first of all, chapter 6, problem 1. This is probably the most difficult one of the ones that were assigned. So to begin with, we start with this data from the book in italics here, these two columns. Those are the raw data. They represent years, so you see by quarter, and then gasoline sales, recorded again by quarter. Okay, I added in as well just this time series. This is just numbering the quarters 1 through 16, and then since it later asks you to project 4 years into the future, 4 more to go to the end of 1999. Sorry, it asks you to project 4 quarters into the future, so I've got 4 more quarters added here. Why do I prefer these numbers to the 1995, 1, 2, 3, and so on? Because we're going to use them in a regression. So for that purpose, then this doesn't work because it has these jumps, 1995.4 to 1996.1. I mean, we know how to interpret that, but with the regression wouldn't. So I turn it into just periods like that, counting up. That's gasoline sales, and we'll start with this. So it asks you, so the actual question says, estimate the linear trend in the data and use it to forecast gasoline sales in the United States in each quarter of 1999. So to estimate the linear trend, you run a regression. It's the linear trend, you assume would be y equals, let's call it y0 plus tx. The point is it's a line of t representing time, and then x some unknown. Let's call it bt. Actually, b seems more like a coefficient. Y0 plus bt. So b would be some absolute rate of increase in gasoline sales, and then t would be the time. Okay. So that's our data. Now we estimate this using a regression. Data analysis, regression. Okay. Input y range, we pick gasoline sales because gasoline sales are the dependent variable. X range, we pick the time, numbered in my special fashion, because that's the independent variable that we think is determining it. And so then if I were actually going to run this, I would press OK and it would generate a sheet. But I've already run it, so I'm going to cancel that and use the one I've already made, which is here. And that gives us a number of variables are important here. One of them is the r squared is somewhat important, but particularly the intercept and the x variable. Those ones actually paste in here because I'm going to use them then to construct the linear trend. So 6.1a, that's for 6.1a, and you notice the key is the formulas here. The formulas represented up here, and b24 plus b25 times b2. So this is, in terms of this is y0, and this is b. I was saying at the beginning of the period, so if we count this as 1, at period 0 would have been this. 22,092.55, roughly. That's an estimate. And then in each period we expect it to increase by 117.075. And then so we end up with this formula, and then we can drag this down. Notice we can drag it past the gasoline sale, so making the projection into the future is really easy. It's almost the same process. Once you've established the trend, you can project it into the future or the past as much as you want very easily. So So these then are predictions for 1999. And, I mean, they'll probably be at least in the ballpark, just because all these figures seem to be kind of in the same area, so, okay, now let's do, so that's 6.1a. 6.1b asks, estimate the log linear trend in the data and use it to forecast gasoline sales in the United States in each quarter of 1999. So, exactly the same words as as part A, except it says now log linear trend. What does that mean? That means that you, instead of regressing sales against time, you regress log of sales against time. So how does that change things? Well, I've written a few equations here that hopefully will shed some light on that. So the equation for the log linear relationship is this one, this y equals s. Am I being inconsistent here? Well, whatever. I mean, s. So it's some starting place. I think s is for starting place. 1 plus g. G is growth rate. So so it starts somewhere and then it grows by the growth rate g each turn. So in other words, or each period. So after each period, then it will be, on average, what it was before times 1 plus g. So, and then that's taken, and then the 1 plus g is taken to the power of t, because the more time it's had to grow, the larger it is, assuming that g is positive. In any case, the further it will deviate from its original value. But, so that's the log linear. And now the difficulty with this expression, you can't run a regression on this, because all this stuff is multiplied together. Regressions, just the nature of regressions is they look for the line of best fit. They're always looking for lines. Regressions can't really, at least it isn't a built-in feature of them to do so. You have to kind of toy with them a little bit to make them work this way. Regressions aren't inherently designed to find nonlinear relationships, which is what we're here postulating that the real trend in gasoline sales probably has. So, that's the log linear, sort of a general statement of the log linear estimate. We take logs of both sides in order to turn this into something where a regression could be run. And logs, this is what they do. They turn, first of all, y turns into log y, or ln stands for natural logarithm. So, so if you don't hear anything else about log, it's usually that's what it means. It's log. You notice that this is here over here. I've calculated ln, natural logarithm, of all the numbers in the gasoline column. So, so there I'm doing the same thing. But okay, so the natural logarithm of y is then equal to the natural logarithm of the starting place plus t plus, you notice that the multiplication turned into addition, and the t, which was an exponent, now turned into a coefficient. So it's kind of bringing everything down a level. Multiplication turns into addition, exponents turn into coefficients. So, now we can run a regression, and the intercept will tell us ln y, and the coefficient will tell us ln 1 plus g. And then we can plug those in, and then we take e to both sides, and we end up getting back to our original expression, except that if you wanted to do the full thing, you'd have to have hats and all this stuff, which, I mean, Excel has that only in the insert equations mode, and that takes really, it's slow to use. So I didn't bother to make all of that explicit, but hopefully you can kind of fill in the gaps here. Okay, so, well, this is what we do here. So we've got our intercept, 10. We've got our x variable, this 0.00484 thing. So we take the log, so if we take the anti-log, And then let me convey this concept of an anti-log. exp, and I'll put it on this, use that as the argument of this function, and boom, what do I get? I get this back. This exp function is the inverse of log. So that reverses that. So I use exp here, exp times this 10. And that's really the exponential function, e to the power of 10.0395 times e to the power of 0.004874 taken to the power of b2. So this is where time comes in. Time shows up as the exponent of this expression. Now, just so you know, this number can basically be interpreted as a growth rate, and I'll show you if I'm typing in a bunch of values here. If they're very small, then the log basically gives you the same thing as if you'd added. Oh, whoops! Sorry, it's the other way around. Or, actually, I guess I could do it this way. So, the log of 1 plus that returns the same thing. And it's slightly less true here. So, the relationship starts to break down. I mean, if you go out to something like this, it's just no longer true at all. So you see 0.8 gives you, but for small values you can actually just say, look at that and say, okay, the growth rate is 4.9%, and that'll basically be right. But strictly speaking, you need to take this log of it, and then it gives you 1 plus the growth rate. Anyway, okay, so having done that, then I drag this all the way down, fill in this column, and that's my log linear trend. So now, C says which form of the trend fits the historical data better. Now I've plotted these so that you can see that. I think there's no substitute really for just seeing it. Although I guess you can't actually answer which fits the historical data better by looking at that. You'd actually have to look at the r squared. So look at the two r squareds. And the linear regression in this case gets a slightly higher r squared, so it seems to work a little better that way. It has a slightly higher t statistic too. The linear fits the data slightly better, but there's virtually no difference. 42% to 41.5. It's basically a toss up between the two methods. Over a longer term, it's probably more likely that the log linear trend would work. I mean, I don't know about this particular market, but in general, I think that would be the case. But if you compare the three, you notice that they're kind of in the ballpark, and they do seem to be tracking the direction in which this trend is going. There is actually sort of a clear trend for this particular data series. But they don't match any of the up and down fluctuations very well at all. That's why this r squared is 42%. Only 42% of the variation is explained. So it explains the trend part, but not this seasonal fluctuation, which is obviously an important part of the story here. So just calculating the secular trend would not be a particularly good way to estimate this data, especially if you're not. Especially if you're really interested in these short-run fluctuations. I mean, maybe if you're thinking way long-term, then maybe you don't care about the fluctuations, but for the short-term, that's going to matter a lot. And furthermore, they're pretty regular, so you could actually compensate for that using the seasonal adjustment method that we talk about, for example. So this wouldn't be a particularly good way of estimating this data, but maybe it would be adequate for some purposes. And see which form trends fits the historical data better, and also why would we expect both forecasts to be rather poor? The answer is they don't take seasonal adjustment into account at all. So that's the issue. Okay, So then, let's move on to 6.5. Using the index with 1985 equals 100 on housing starts in the United States per year from 1986 to 1997, given in the table below, forecast the index for 1998 using a 3-year and a 5-year moving average. These are pretty simple methods of projection. I mean, they can sometimes work pretty well, but they are definitely simple, even to the point of crudity. So 3-year moving average, just look at the past 3 years, and then you project this year will be similar to previous years. 5-year moving average, same thing, except they use 5 years instead of 3. So you can think about the relative advantages and disadvantages of a 3-year and a 5-year moving average. 3-year is going to be more volatile because every new movement in the data can shift it around. But the 5 years are going to be using more out-of-date information. So if you have a market that's moving fairly quickly, to assume that it's a moving average that reaches all the way back 5 years into the past, that might not be a very useful way of looking at this particular problem. So, but in any case, and for this they then ask, which of your estimates is better if the actual index of housing starts in the United States for 1998 is 163? So I've thrown that in here. So this is, maybe I should set it apart. That's actually new data. That's just, or rather forecast. That's future data. We don't see it yet. These are the forecasts we made. Because they're both too low. So you can think about why. I mean, the past 3 years, 142, 156, 162, so that's the average, but it seems like there's a big growth spurt going on, so to expect that that will suddenly be reversed, maybe not such a good assumption, but of course that sometimes that does happen. Maybe you'd use this method and you'd accurately recognize a bubble, but the 146.2, this does not perform as well. It's reaching further into the past, so it's including things like 1993 in its average. Well, maybe that's not so relevant anymore, and in this case, the 3-year moving average works better. But if there's lots of sort of long-run volatility, sort of moderate, medium-run volatility, say, then possibly a 5-year moving average could work better because you'd become less sensitive to recent fluctuations that were likely to be reversed. It all just depends on the time series. There's no real strong theoretical reason to prefer this method. In fact, it's hard to see in theory exactly why the 3-year moving average would be useful at all, but I guess it compensates for recent fluctuations, and it's much easier to use, of course, than a regression, and doesn't have as much work to do with specifying regression equations and stuff like that. Okay, so 8. Serial sales. And so we have 3 time series in addition to serial sales, and we're interested in whether each time series is coincident, leading or lagging. Now I'm sure there would be complicated scientific ways to do this, but we didn't really go into them even in the textbook, so I won't bother with those. This is basically just eyeballing it. 110, 50, 130, 60, 125, 56, 120, 54, 130, 60. If you notice, every time this goes up too. And to some extent even by similar margin. So this is a relatively small drop, this is a relatively small drop, this is another small drop, another small drop. Rise, rise, maybe similar scale. Slight rise, so it's pretty much doing the same thing as the main time series. It's a coincident indicator. Time period B, this one's the hardest to figure out. It takes some looking before you get it. Okay, 125 down to 120, 140 down to 130, 120 to 130, 130 to 145, and finally 130 to 135. You go back to 145 to 150. So interestingly, these all match up 2 months ahead. So the basic size of the movements and seems to match up, or 2 months. So this is a leading indicator. So C, here you can see this rises a bunch, then this rises a bunch. This drops a bit, then this drops a bit. This drops. Let's see. Oh, this drops a bit. This drops a bit. And then we can't really say. Oh yeah, we can. That rises. That rises. It's basically just a matter of matching up what rises and what falls when. And of course, there are computational methods to solve this problem. Which, if this was really important to a business, they might start doing that. But many times people will rely on kind of cruder methods because they don't depend as much on data and they're easier to understand, and so then you could end up with just kind of eyeballing it, just looking at the chart and seeing if we can figure out how the numbers seem to be related. Okay, so 7. Now we're on to chapter 7. Question 1 here. So assume that L1 equals 1 and L2 equals 6, while K1 equals 1 and K2 equals 4 in figure 7.2, and indicate the number of units to which A, F, E, B, BA, and DC, DC. It just occurs to me, I didn't think of this until now, but that I think we actually have that figure in the slides, so I can display it here. Sorry. Wrong PowerPoints. Let's go back here to chapter 7. Apologies. And then we can scroll down to this. This is what we're talking about here. So, it says, assume that L1 equals 1 and L2 equals 6, while K1 equals 1 and K2 equals 4. So L1 equals 1 and K2 and L2 equals 6, K1 equals 1, K2 equals 4. So this is one labor for capital at point F. Well, point F is a vector of endowments, or a vector of inputs. Fe shows us the volume of outputs. So if we go back to our table, we've got L equals 1, K equals 4, we get 12, which is the answer here. In the same fashion, it next asks for BA, this line segment. So it's told us this is 1 and this is 6. So we can go up 2 slides. 1, 6. That again is 12. And then finally it asks us for line segment DC. So that would be 4 capital, 6 labor. So that's 36. So that's what appears in my answers here. But I haven't done any explanation because it's hard to explain it. But that's what that's what this video is for. Okay. So now move on to 2. And I guess this one's actually in the back of the book. It's interesting. Maybe I should see whether my answer agrees with theirs. Um, let's see. Table 3. And yeah, okay. Oh, except I didn't draw the curves. Well, that's okay. I'll do that now. Have a chance to show you how to do it. So, total. This is just taken directly from the table. I guess it's from this table now that we have it up. So we're told to assume capital is at 4 units. So then we get 12, 28, 36, 40, 40, 36, which is exactly what shows up in this column. And from there we can calculate average product equals total product over labor. So we divide these, and notice the formula here, B3 over A3, B3 over A3. That drags down 4, 5, 6, 7. It's always dividing total product by labor. The marginal product is the change in total product divided by the change in labor. I put this here for completeness. Of course, in this case it's always 1. But, so total product increases by 12. 12 appears here. Total product increases by 16. 16 appears here, and so on. Now, for output elasticity of labor, there happens to be a formula. So AT divided by MP, or no, sorry, MP divided by AP. And you can figure that out if you imagine. Just this delta TP divided by P, that's the percentage change in total product. Delta L over L, that's the percentage change in labor. The ratio of a percentage change in one thing to the percentage change of something else is generally called elasticity. So, so we can calculate those elasticities, and then if we chart it, start with a chart of, I'm going to do scatter plots this time. Start with a scatter plot there. Let's take away the markers and sort of smooth it out. Not perfectly smooth, but that's okay. And then call that TP. So total product. Then we're also interested in average and marginal cost of labor. So let's start by inserting the average cost. And so we can connect all that up. And then we'll add the marginal cost. Oops, sorry. So we'll call this marginal cost. These X values, again, labor. And then here, marginal cost. And notice marginal cost actually goes negative. So that's the. So I think that's the answer to 2 here. Well, so it says draw a figure similar to figure at 7.4. then how do the results in parts A and B differ from those in table 7.2 and figure 7.4 in the text? So figure 7.2 is this one. Figure 7.4 does it appear here? Yeah, it's this one. And so how do they resemble them? How do they differ? Well, for one thing, I mean, I guess they're not curved, and yeah, they're actually pretty similar. Let me just check quickly what the back of the book gives as an answer to that question. See what differences they noticed. So it says, well, capital is fixed for both MPL and APL are both greater when capital is held constant in 1 unit. Yeah, so you get more product of labor, and then diminishing returns set in later for that level of capital. So I'll finish this up in another video. All right.